Very good morning to all of you. Uh, Thank you for joining the webinar on time. So we had a very good participant right now. We'll start with the webinar. So before starting with the actual technical background, let me just quickly introduce about myself. Myself, Piyush Vishwanaduri. I look after the CA domain in Beacon SolidWorks. I have been in the CA domain for last 5 years, or I can say 5+ years. Today, we are going to more focus on the FEA domain inside the CA tool, majorly on the advanced tools what are present inside 3D experience simulation. So even before beginning with that, today's webinar is powered by GoToWebinar, where you can see on the right, you will get an option where you can tell the software, where you can write a question. Let's say if you have any query regarding the presentation, what we are going on, or you have anything else, you can write the question. And at the end of the session, we'll be opening up for the Q&A session for you. So quick look after the agenda for today. So we'll start with the introduction to the 3D experience simulation. We'll see how easily we can connect it with our existing 3D CAD, SolidWorks 3D CAD software and do a particular analysis. We'll see some of the wow tools. One of them is with the multi-step analysis, mesh techniques, which include like mesh to assembly or hexagonal meshes. We'll also see a glimpse about something called as a general contact and how it can be used, and another thing is called as a cloud computing. At the end of the day, we'll start with the Q&A session for the same. So simulation, earlier, it was very hard to use. It was very complex. It was very expensive. We had a very limited computer power long back ago, and also it was very long time iterative solving. But today, as we are going over a democratization, it is very powerful, very easy to use. It is very we can say very easily we can visualize how the analysis is going or what is happening in the background. It is very cost effective. It is totally integrated in the 3D CAD software, which you can utilize and make some parametric optimization. And also, as we are moving further, we also have something called as the cloud computing, which we can utilize to solve a particular complex or a very hardcore analysis in a minutes or we can say an hour. Evolving needs, as you know that earlier, as we know that as the analysis are going more complex and in larger scale, the need for computer is also going high. Also, the result should be as fast as we can get without any affecting the accuracy. Or we should have the flexibility where can we use or how it can be used or how easily we can use it. We should have the knowledge of the tool. With 3D experience simulation, with the powered by the Abacus CA tool, we can easily do a particular analysis. It can be any type of analysis, starting with a very basic like a nonlinear or a multi-physics where we are doing a coupling analysis. Using the HPC cloud computing, we can easily access more CPU cores where our limitation of a hardware is being totally solved. It is being a subscription model. We can subscribe it for a particular time period. Let's say if you have any particular project which is in a prior basis, you can subscribe it, we can use it, and then it is again closed for you. Totally integrated with a CAD environment, whether it is SolidWorks, CATIA, or any other 3D CAD platform which can be easily collaborated. Apart from that, we have something called as a collaborative space as a platform as a service where we can collaborate and share the result with other users or from the same company. So here are some of the glimpses how SIMULIA tool is being trusted all over the world. It is one of the leading FEA and the CFD software where we can do a realistic simulation of a multi-physics, do a CFD analysis to understand how the flow is happening or how the parameters are getting generated. Or we can also do a coupling analysis where we can understand due to the structural what is the effect on the flow or a two-way FSI we can say for that. So just a quick introduction of a 3D experience simulation. It's a well-known Abacus integrated tool called as SIMULIA Abacus. It is very fast, robust. It has high level of contact generation tools like general contact is there, or we can create a manual contact also called the contact web. It has total capability where we can control how the mesh should be. We can check whether the mesh created by us, is it good quality, or there is some area where we can do some refinement. Apart from that, we also have a tool called as a material modeling where we can create a material from A to Z. We have very inbuilt material modeling tools according to the type of material we are going to analyze. We can integrate it totally inside SolidWorks or CATIA or any other 3D CAD platform which we can utilize to just do a parametric analysis. As we said earlier, we can do any cloud-based solving also for a particular large assembly or a model. As I said earlier, it is very well-known software for a non-linear analysis where you want to do analysis on a particular rubber part or a plastic part, where there is a complexity in the contact or there is a very large deformation happening. So as we know that there is a very large material library available with us, where you can rubber material, which is generally a hyperelastic, or a plastic or elastic behavior of a material. General ideal case for like sealing, pressure, rubber bushings, or also want to understand how the preloading on a bolting can affect the analysis. So we'll start with the first topic where we'll understand how we can easily connect with our existing SolidWorks 3D CAD and how we can do a particular analysis, make some design changes in between and rerun the analysis. So we'll start by opening a particular assembly. In our case, it is a crank design. We'll create the FEM. So it stands for Finite Element Meshing representation, which includes the mesh, its cross section, and what is the type of, whether it is a solid element, whether it is a shell element. And then we can also define the material in the same. Apart from that, we also define the connection, how the components are going to interact, whether they are totally bonded or is there any clearance or a friction going to happen between them. Once that is done, we'll shift it to a scenario creation where we'd apply the boundary condition, additional context if required, and we will then run the analysis on a local cloud and understand how the results are going to appear due to the particular loading condition. And let's say in between we got to know that there is some design changes required, we can quickly shift to SolidWorks, make those design changes and come back to a 3D experience simulation and understand how these changes are going to affect our analysis. So here you can see this is my SolidWorks environment where there is a three-part crank design. What we are going to do, we are going to first shift this particular analysis to our 3D experience cloud platform. So just by 2 clicks, we can quickly save this data on a cloud and transfer it to our SIMULIA converter. So once the data is saved, we can open this particular assembly or a part in our native app that is called as a 3D experience. So again, it has various types of apps as you see on the left, on the right, that is there is a various types of roles or various types of apps present here. Once you reach to the particular app, you can create by starting by creating a FEM, that is a finite element mesh, just by selecting what are the components are going to take in the part in the analysis, what type of meshing we are going to use. Like here, we will first, let's change the name of FEM. We'll keep the name as a crank design. Then we'll start by defining the meshing. So either I can use the default mesh for all the cases, or we can define the mesh one by one on a particular part. So we will go in detail about how we can create the mesh in the further as we go for the presentation. So here you can see we have something called as a tetrahedron mesh, which generally generate the mesh at the surface at first, and then it fills out the inner boundary. Here we have a total control, like what will be the mesh size, what will be the absolute stack, which actually controls how the geometry is purely captured with respect to the actual geometry in the mesh. Apart from that, we can also have some local mesh specification, like in some area, we require the mesh to be refined. So we can provide the local mesh setting. Like in this case, the area where there is a rib cut out, we will define a 0.5 mm mesh setting in that. And by just one single click, we can quickly check how the mesh is getting updated due to the local refinement in that particular area. As we move forward, We'll also check, we'll also add some other mesh technique to the other parts. So here, as you can see at the bottom, there are various tools available for creating mesh. To cover all those tools in a single webinar is not possible. So we'll see if we can have in future a dedicated webinar where we can understand how the meshing techniques which are available inside SolidWorks simulation, 3D experience simulation. Sorry for my bad. So once the FEM has been created, we can apply the boundary properties like whether the geometry is solid, whether it is shell or it is a beam. Apart from that, we can also apply the material. So 3D experience, we have the inbuilt material available with us, which you can utilize, or else you can also create your own material. Like in my current case, I have created a material named as alloy steel and will be using that material in our particular analysis. So this material we can apply on a particular single part on a FEM mesh on a particular multi-body or a single body, or you can directly apply to a main assembly. Like in my case, I'm going to apply it on my main assembly. So once this is done, we'll apply the body properties. So by default, all the three bodies which are present are solid in nature. So we'll just quickly select those and tell the software that these are my solid geometries. And at last, we'll define some connection like the paddle and my main crank is being welded together. So I'll tell the software, find out the area where there is a bonded contact or a tie detection in 3D experience. So using the tie detection tool, we can quickly check where is the area we want to create a tie. We can create on a whole geometry or we can create on a particular multi-bodies. Once this is done, we can switch to scenario creation app where we can define the boundary condition, what type of analysis we are going to perform or how they are going to interact with one another. We'll quickly create a new study here. I'll name it as Screen New Sim. We'll use the default FEM what we have created earlier, or we have the option where we can create a new FEM in this particular window also. So once we have gone to our new simulation, we'll start by defining what type of analysis we are going to perform. So in this case, we are going to start with the static perturbation, which is generally our linear static analysis. We'll start by defining the boundary conditions. Like in my case, it is being hinged at the 5 locations. So I'll quickly define the hinge joint on all the 5 cylinder which is present. Additional to this, there is a center cylinder which is also being radially, which is being also axially restricted. So I'll also select that particular back area cylinder to be axially radiated by a hinge fixture. Then we'll apply a load. So the pedal load will be applied on the one end. So just by selecting the type of load, where it is acting, or what is the orientation of load, or what is the amplitude of load, we can tell the software how the boundary condition are defined. We can use the global coordinate, or we can also create a local coordinate in that area to define the loading condition or a loading direction. At the end, there is something called as a general contact. We will see in the detail later on how we can utilize that general contact. I'll just apply that general contact quickly. And at last, we'll just run the analysis. Now, after running the analysis, we got to know due to the bending load on a crank, there is some stress is generating at a near the crank area. So I want to increase, let's say, some dimensional change in that area. So the current fillet, what we have applied here is around 0.2 mm or 0.5 mm. And I have to make the changes so that it is being increased so that the stresses which are getting generated there will be reduced. So I can quickly jump to SolidWorks, reserve that particular geometry. It may be a part or assembly. Make the changes. Like in this case, the radius was around 0.5 mm. So I can quickly reserve that geometry inside the same PLM connector. Let's say if I want to reserve the part, I can quickly log the part. So I can make the changes. So those won't be affected by the other part who are using it. And since we are in a SolidWorks environment, we have a total control over the geometry. We can make the changes as per our requirement wherever required. So I'll make it around 2 mm. And once we made the design changes, we can come back to our platform, and we can, or our tool, and we can update those changes in our geometry. And since the simulation has been already created, so here before going forward, we'll just unlock it and save the data on the cloud so that it get updated in the actual cloud also. So here you have the option where you can save it as a new file, or create a new revision, or update or upload, or we can say duplicate on the original file. So once this is done, you can also see the conversion status. Once it is okay to go, we'll come back to our SIMULIA platform, where you can see the update has been carried out. Let me quickly zoom in that area, and you can see there's the fillet has been updated. Now, once this is done, we can recreate the mesh and rerun the analysis. So apart from that, all other associativity with the boundary condition is being not being affected. We can also add some local mesh to capture that area with some refinement. So you can see that it is little bit coarser mesh in that area. At any time, we can edit a particular mesh. Like in this case, I'll just quickly edit this particular mesh, apply some local mesh settings in that particular fillet area. So here I can select faces manually, or I can, let's say I can create a group of such faces so that it can be utilized more than one times. Or else I can also use something called as a propagation tool, where I can tell the software to select a tangency, or select a tangency with respect to some angle or something. So once we have defined the mesh control, we can recreate the mesh to see the update on the particular geometry. And then we can quickly move forward and simulate the same analysis again. So we are okay to go. We'll now go forward and run the analysis and check the result for the same. So just you have to jump again to our scenario app. So these apps are, as you can see here, are connected like model, scenario, and result. So you can jump from one app to another app at any time. Now, as you see here, there is a drastic change in the result. Earlier it was around 4 or 650. Now it has been reduced to around 393. So this way, using the connectivity with the SOLIDWORKS simulation, SOLIDWORKS CAD environment, we can quickly do the changes and come back to our native app or the SIMULIA app, where we can check what are the effects due to that current changes. So in the previous example, we talked something about called as the general contact. So general contact is very helpful where there is no tie or a bonded contact between the component. So it takes into effect all the contacts. We have a two approach here. Either we can create the contact manually between multiple components, as you see on the left bottom. Let's say there are multiple components, and you want to create a context. We can create those contact mentally or by some detection tool. Or there is something called a general contact, where I can tell the software take all the geometry which is present, and maybe it is currently touching, or maybe there is a gap between them, and while the performing analysis or while applying the load, they are going to touch to one another. So that phenomena can be taken into easily into the general contact, where we can define what is the friction, or what is the friction going to apply, or how they're going to slide. Is there any self contact going to happen? So that totally is being triggered inside the general contact. As you can see on the right, where we are seeing the crushing of a beam, it is generally done by a single contact using the general contact tool. Next, we'll see something called as a multi-step analysis. Now, this is one of the wow tool what I have understood inside this particular platform, is that the multi-step analysis, where we can do a multiple step analysis. Like in this case, you can see on the screen. First, we'll be doing a, like in the bowstring case, there is a pre-tensioning happening in the bowstring. Then with the arrow, we are pulling it back. We are also going to investigate when we pull it back due to the tension, what is the natural frequency or how it is getting updated. And at the end, we are going to release the bowstring. So this total setup can be done inside a single window called as analysis case, where you can create the multi-step analysis one by one. It can be a linear perturbation or it can be a non-linear static analysis. So there is some cases like in our case, we'll see an example of a creep analysis. We're starting with the basic static analysis and then we'll going to the creep analysis. So let me quickly open the model. So I have the creep analysis model intersection pipe available with us. I'll just quickly open it. We have, for our case, we have already created the mesh or FEM, we can say, for that particular geometry with the material and the properties already defined. So once the model is open, we can quickly jump to our actual geometry where we can upload, we can also tell the software to also open the representation which is attached to this particular geometry. That is our FEM. So once the model is open, we can then switch to our scenario app where we can tell the software we want to create a multi-step analysis. So in multi-step analysis, we are going to start by defining the name of a simulation. We are going to do a pipe analysis. I'll name it as pipe sim. We can select what FEM we are going to use. So we have already created FEM. We'll just switch or select that particular FEM. Here you can see this is my analysis case one. We'll start by defining procedure. So I'll start by defining a linear static analysis first, where I'll define the maximum time step. We'll name this first step or first analysis as a pressure analysis. Since we are not going to take the geometrical nonlinearity, we'll uncheck this particular option. And apart from that, we'll keep all the other options same. After that, we'll do a creep analysis. We'll name this as a creep. We'll define what is the maximum time. So we'll do for a 5-year analysis. So I'll name 5 and for year, I'll type A. So it will automatically take the 5 as a value and the A as a year. For initial time increment, we can type 1 hour, minimum 1 hour, maximum time increment again 5 year, and then what is the maximum creep rate increment. So once we define the incrementation for the creep factor, we can move forward and start by defining the boundary condition. So let's move again to our main analysis, that is the pressure step. Here we'll define the symmetry. Since this is the actual pipe with only the 1/4 section, we'll start by defining symmetry on the 2 planes. So this is my first symmetry. Second symmetry on the other side. We'll name this as symmetry 2. And the pipe is being pinned or flanged at the top. So we'll keep a fixed displacement. We'll restrict the Z direction movement of the particular pipe top end. So as you can see at the bottom, there are various restrictions which you can use. Then we'll move further and we'll apply the loading. So starting with the pressure load, which will be internal pressure on acting in the geometry. So here we can select or we can name this as the internal pressure, and let's apply the faces, like in this case these 2 faces, and the value of the pressure in this particular geometry. At any time, let's say if you want to do some changes in the pressure, you can edit this in a feature manager which is present and make the changes as per your requirement. Same way, there is some other type of pressure, that is the end vessel or end cap pressure is acting on another end, which is in tensile in nature. So I'll apply that pressure and we can define the magnitude either negative directly there, or we can change the scale factor from 1 to -1. So both will give you the same results. We will also apply the initial temperature to the geometry, since we are doing a creep analysis, so that will make a change. This will make an effect on our analysis. So once this is done, we can go forward and check all the things which we have defined. Apart from that, we also want to check what is the output. So I want to get output of a creep equivalent strain. I can use that particular parameter as output, and we can check what are the feature or what are the boundary condition, other parameter which we have created inside the same scenario. So once this is done, we can quickly run the analysis and check the results, whether it is for a first step, that is the pressure analysis, where we can understand what is the pressure inside it, or whether it is the creep analysis, where we can understand what is the stresses getting generated. Or like here, you can see in the pressure step, there is a von Mises stress of around 1.1 e raised to 8 and displacement of around 0.04 mm. In the creep step, we can check what is the displacement or one message generated at a particular time step. At any time, I can plot the maximum, minimum, or I can also use the probe tool to calculate at a particular location. Apart from that, let's say if we want to plot other things like the creep strain, what we can do, we can use a tool called as a plot command manager at the bottom and plot a new plot called as contour plot, from which we can select what type of plot you want to plot. So here I'll select the equivalent creep strain. I can define other things like what is the scaling factor, whether you want to see the mesh or not, we want to see the element value or a node value. And let's say I want to check at the last time step, what is the creep strain in that particular location. So the maximum creep, you can see it is around 0.00562 at the near the tip of the intersection of two pipes. So such way, using a multi-step analysis, we can perform analysis which is equivalent to a real scenario, where we can understand how the actual scenario will be affecting the geometry or how the affecting the plastic strain. Next, we are going to see, or we can say, we are going to actually just scratch a little bit surface of something called as a mesh technique. As a mesh, as a tool, or as a whole topic is very vast. We are going to only check some of the tools which are present in that. And in the further coming days or maybe coming month or a week, we will have another webinar where we can where we will see the advanced meshing techniques in detail in the whole webinar. So meshing, we have a various options starting with like a tetrahedron mesh or octatetrahedron, or we can say the basic brick element which you can use. Meshing can be done in a solid way, in a shelling or a membrane, or also in a 1D or a 1D cases. There is some tool called as a mesh of assembly and assembly of mesh, which is one of the well-known tool in 3D experience simulation. Now we are well versed with something called as mesh of an assembly, where we generally open a particular assembly, create the mesh part by part, and use it for our analysis. There is another tool called as assembly of mesh, where what we do, we open the particular parts, we create the mesh for individual part according to our requirement, apply the local meshing setting or apply the changes, and then assemble those all mesh into a single geometry. So how this tool works, let me open an example here. So here we are going to see an example of a car jet. So you can see we can quickly open or search a particular geometry inside a 3D experience platform. We can open that or we can explore it. Here you can see this is my car jack assembly, which consists of various parts. Some of the parts like the side support are repetitive in nature, or they have multiple instances. Even the side supports are repetitive, links are repetitive. So in such case where the number of components or instances are much, we can use a tool called as mesh or assembly of mesh. Okay. And here it's not restricted like what type of tool we are using. We can use both the tool as a combination also. So let's start by creating a model creation here and defining the meshes for one by one. So here we have something called as a contributing FEM, where you can see the various parts which are going to take part in the analysis. At any time, I can tell the software I want to create a part or a part level mesh. I can right click and tell the software to create a FEM for that. It will also tell you where these instances are repeating, and it will automatically reuse that particular mesh control. Let me open that particular part separately in a window where you can see the FEM has been automatically added. We can jump to that FEM, add some mesh control. Like in this case, it is a simple geometry. So we'll use something called as the 3D sweep mesh. Just select the geometry. Software has automatically selected the source and target, which you can control by our end also. We can define the mesh size and how many layers you want to create, what type of mesh, whether it is a linear or a quadratic mesh you want. That can be controlled in a single window. Once this is done, I'll just say mesh. So it will create a mesh for me. And you can see it has added those 3 layers in along the thickness. I'll close this part. And as you can see in the my assembly window, all the 4 links are now meshed with the same mesh FEM which we have created. So this FEM can be created at the assembly level by defining a new FEM, or we can open the part individually in a separate window and tell the software to create a FEM for that. So like here, we can see the link we have created a separate window. Again, we are going to use same sweep 3D option and create the mesh for the same. But now what happens if I create it individually? It does not get updated in my main assembly. So for such case, I can go back again to my contributing FEA element, and it will tell me that some of the candidates have already FEM present in it. So either I can select manually one by one, or I can directly select the main column and tell the software to automatically import all the existing FEM present inside the particular assembly. So now you can see the icon has been updated, and also the visual of our graphic window has updated with all the updated mesh. We'll again apply some mesh control to the side sprocket or a side support. So we'll create the mesh, and you can see it has updated for all the instances present with us. Let me open that particular assembly in a separate window and go in our FEM mode. So apart from tetrahedron or a sweep 3 mesh, we also have something called the octatetrahedron, which we can utilize to create a mesh. So what it does, it creates the mesh internally first, and then it comes outside to create the surface mesh. So it is like our traditional sort of simulation mesh what we use. There is something called as the absolute sag, which controls how the mesh is refined with respect to the boundary condition. We can also apply the local mesh settings. These settings is same for all the type of mesh control what we are using right now, whether it is hex dominant, octatetrahedron, or a normal tetrahedron, or even a sweep 3D. So since we have created the mesh, if we go back again to our main assembly, it get updated here. We can also create mesh directly at our parent or the assembly level by just double clicking the parent FEM, which is our current, and telling the software what type of mesh we require. Like in this case, we'll see an example where we are using a hex dominant mesh, where we can select the body or a support, define what is the maximum minimum size. We can also apply some local refinement if we want, or we can tell the area or a volume where we want to create a local refinement. And in a quick second, it will create the mesh for me with the hex dominant or a hexahedral element present in that. Apart from that, we can apply the mesh control to other parts, like we have already seen example for a tetrahedron and octatetrahedron. Let's again see an example for a octatetrahedron where we have selected the screw rod which is present and quickly created the mesh for the same. Last, there is a top part which we need to mesh. So I'll be using a tetrahedron. So it has some refinement, or we can say some detailing. So we can use tetrahedron mesh. So the major difference between tetrahedron and octatetrahedron is the reversal. Tetrahedron mesh does the meshing at a surface level first and captures the volume, while octatetrahedron do the vice versa. It captures the volume first and goes to the surface level. Once we created the mesh, at any time we can use something called as a mesh sectioning, where we can understand how the mesh is being created internally. Or we can also use a clipping box to create a manually oriented clipping, where we want to understand how the mesh are being created internally. As you can see in the supporting rod, how the mesh are being created. We can also go something called as a quality check, where it will tell what is the aspect ratio, how many elements are distorted. We can check how they are connected, what is the maximum angle, how their skewness, what is the percentage of angle element which are skewed. At any time, I can select a particular area, like I selected a poor area, and it will show me where are the elements which are in poor cases. Like in this case, if I zoom in the base of the part where I've created hexagonal mesh, you can see there are some elements which are in poor quality. We can also check the area or what type of mesh element we have used, like whether it is a wedge, whether it is a tetrahedral with a 4 node or a 10 node, by just selecting a particular window, and it will tell where are those elements present in our analysis. Apart from that, we can also set the criteria like how the good, poor, bad quality are managed. So this criteria can be set by us and saved for our case for other type of analysis also. So as I said earlier, we are just seeing a quick overview or a glimpse of the mesh capability present here. In the upcoming webinar, we'll also see in detail what are the types of meshing setting we have here. Parallel to that, we have something called as a cloud computing available with our 3D experience simulation. So let's say if your geometry is very complex and required a very high computing power, which is limited to our hardware current present with us. So we have a paid version of cloud computing where we can actually do a cloud computing up to a 144 core. We can use in that we have a control like we can use a credit system or we can use a token system. As you can see on the right on a particular image, what is the time required to solve this particular drop test of a camera with a single core, with a 4 core, with a octa core, or with a 18 or even with a 36 core. So since we are limited with a 4 core or 8 core in a particular system, we can go for a cloud computing, which can help us to reduce the time by around 90 to 95% also. So if I talk about the credit and the token system, so credit is like a one-time use or a short-term use for a 1 or a 2 type of analysis. Once it is used, it is totally consumable. You do not get back in our particular unit system again. Vice versa to that, token system is like we can say you utilize and come back to us. So let's say it's like an SNL, what we call in SolidWorks. So once you tell the software that you want to do the analysis, we have an option where we can calculate how many tokens are required. And once I say go, it will solve the analysis on a cloud. And those number of tokens. So let's say if I have around 18 or 20 tokens inside my tool, and it required around 10 tokens to solve the analysis. So once I say to solve the analysis, it will utilize those 10 tokens and it won't be available during my computation. And once the analysis is done, it will come back to my locker back. So this was about a quick understanding what is the new features or what is 3D experience simulation tool what we have inside our 3D experience platform. At any time, if you have any queries or let's say if you have any doubt or you want to see in detail how this product can be useful to your particular industry vertical or your particular product design, you can connect with me or you can connect with my colleague Mr. Vivek on the given number or even on the given email ID. Now we are open for our Q&A session. If anyone has a particular questions, you can type in your right chat box. So seems to we have a multiple questions here. That's very good to see. We have an interactive session here. So the first question is the node connectivity in mesh is compatible for two different body? So by default, it is incompatible in nature, but we have the control where I can tell the software to do a compatible between the two components by defining a mesh control or a mesh setting between the two components. So what happened? Let's say there will be a source study where we have created the mesh and there is another target body on which you want to create the mesh. So I can tell on the target body that I want to connect it with my source body. So it automatically will get connected with my source body. Second question I have, is 3D Experience SIMULIA different software than SolidWorks simulation? Of course, sir. So SolidWorks simulation is something different It is powered by console, while 3D Experience Simula is purely powered. 3D Experience Simulation is powered by our SIMULIA technology, and the FEA tool is powered by the Abacus. So SIMULIA is a brand under Dassault system where it has multiple tools like Abacus, Tosca, PowerFlow, XFlow. So one of them is being the Abacus, which is front-end simulation for the front-end tool for a FEA simulation. Presently, we have SOLIDWORKS simulation. Then why to go for 3D Experience Simulia? So 3D Experience Simulia has multiple, and it is a high-end capability tool. SOLIDWORKS simulation on one end is a medium scale tool, where as you know that you don't have much control on the mesh type, or it don't have that control over the non-linearity or even the material modeling. So simulation, 3D Experience Simulia has that capability, like what should be the mesh size, whether it is a tetrahedral or a hexahedral mesh, or how the contexts are getting generated. Even if there is a non-linearity, the solving capability is good inside, or it is well known inside 3D Experience Simulia. Apart from that, we also have some limitation, or we can say some core limitation inside SOLIDWORKS simulation. So it generally don't use multi-core in all the cases, but that is not the case with the 3D Experience Simulia. It use multi-core in all the setup cases also. Next question is, does it include pressure vessel, and is linearization of stress possible? So I have to quick check whether the pressure vessel analysis with the linearization can be possible inside 3D Experience Simulia or not. So let me, I have your email ID. Let me just quickly check, and I'll update you on the mail, sir. Can we do a hex mesh also in this? Yes, sir, we can do a hex dominant mesh where it can be a total hex or the mixture of hex and tetrahedral. How complex we can, how complex part we can mesh with hex mesh? So it can be as complex as possible. We don't are limited to any capability limitation in this. We have a total control. We can also split the geometry into multiple, we can say multiple bodies, and we can tell the software like this is the area where we want to create a hex mesh, and apart from that area where there is a complexity, we can create the normal tetrahedral or octatetrahedral mesh. Can the simulation result be saved to a local machine? So by default, the results are saved in a local machine, but you have a control. If you want to save it on a cloud, you have the control. You can save the result on the cloud so that it can be directly accessed there. So by default, the results are actually saved in a local machine, but you can control whether you want to save it on a cloud or whether you want to save it on a local machine. Next question, what we have is vibration analysis possible in your software? Yes, sir, we have a total control of the vibration analysis, whether it is like a natural frequency study or a high-end random vibration, or you want to calculate the acceleration factor. So that can be done inside the same tool. Well, why was the aspect ratio for some elements so high, up to 187? So what you have what you have shown on the particular screen was not the aspect ratio. It was the count of the element with the aspect ratio. So when around 1,87,420 number of element had the aspect ratio, it was good, while the other had some poor quality. So it was not the value, it was the number of count of the elements. Siddharth sir, I have already answered that question. Simulia is a different tool than what we have till now was the SOLIDWORKS simulation. Yes, we can export this mesh what we have created, and you can use it in the Abacus solver also. So we get the option where you can export the mesh in IMP format, and that IMP format can then be imported in a Abacus CE legacy tool. Mesh compatibility. Can you elaborate regarding what is mesh compatibility? Whether is it possible to stimulate bolt joint stimulation? So whether are you talking about something called as animation, or do you want to do FE analysis? So generally stimulation is a term majorly used in animation purpose. Another question we have, for the system level or enclosed and PCBA, can we use this simulation for load carrying area or part to understand thermal stress and mechanical stresses? So what I understood from your question that you want to perform a thermal or the mechanical or the coupling analysis between the temperature and the thermal or the mechanical load. So yes, that can be done. If your question was something else, I would recommend you can write us down on the below mail so that we can elaborate in more. Can we do stress elimination? So I have to check regarding pressure vessel cases where we have the compatibility where we can do a stress elimination or not. What option do you have for flow simulation, and do you have any technical documentation you can share? So yes, we have something called as fluid dynamics engineer, where we can do transient or a steady state flow simulation or CFD analysis. In the upcoming month, we will have a webinar on that too, also covering the capability of a flow CFD tool inside 3D Experience SIMULIA. And definitely we'll share you with the documentation regarding the key capability present in that. Yes, Siddharth, we will share you with the technical and the pricing section of the same tool with you, sir. So what we would recommend, you mail us down regarding your requirements so that we can first note it down what are the requirement, what type of tool or packages will cover all your requirement, and then we can move forward. Or we can have a detailed demonstration for you in the further cases. Do 3D Experience have its own model creation software? Yes, we can use the CATIA environment inside 3D Experience simulation, 3D Experience environment, and we can do a modeling. Or we can also use the CATIA role to make the changes in the geometry which is being imported from SolidWorks or any other environment. How to mesh and seam in a welded joint with a deformation and material property due to hazardous. So for welding joint, we have something called as connector, whether it is point-to-point connector or a edge-to-edge or a face-to-face connector or even a face-to-edge connector. So those welding joints can be defined here, and we can understand how those welding joints are performing for the given loading condition. Is the contact type between two bodies is independent of generated mesh? Yes, sir. We have a total control of incompatibility, and after that we can define how those two components are going to interact, whether they are totally bonded to one another or they are going to just interact during the analysis. So that is being defined later on using the interaction or the connection definition. This is a pure standalone software. It is not an add-on to a SolidWorks. We have an add-on to SolidWorks called as 3D called as SolidWorks connector or a SolidWorks PAPLM connector, where you can transfer the data from SolidWorks to that particular standalone software. Is fatigue model harmonic analysis supported? Yes, we are support. We have the support for fatigue analysis inside the same window. We have a role called as a durability engineer. A model and harmonic are supported in the same environment what we have showcased. Is nonlinear contact analysis without node bonding possible? Of course, sir, what we have showcased in this case, where some of the nonlinear analysis where we do not made any compatible mesh, the node-to-node connectivity can be totally controlled by the contact what we have defined. Can we use this software for gear mesh? So gear mesh, if you're talking about actually animating the gear, so for that we have some other solution. And if you're talking about the FEA front to create the mesh of the gear, then yes, it can be done. Is it more compatible for welded structure analysis? Yes, sir. So we have a control what type of properties you want, whether it is you want to do a solid analysis, you want to do a shell membrane analysis, or you want to do a pure structure analysis or a mixed meshing. So that control we have. So let's say if you're talking about a welded structure analysis, we can do a beam analysis where we can define how those node-to-node beams are connected. What all 3D modeling software can export 3D model for analysis? So all the desktop oriented softwares which are installed desktoply or where you can create the modeling can be connected with the current tool, that is the SIMULIA tool, or else you can convert those files into a neutral file like a step IGS or a Parasolid, and then you can import it in our particular tool. Harmonic analysis, yes, harmonic analysis is possible. Pretension analysis of a bolting is possible, where we can take the actual CAD bolt and define a pretension, or we can use a connector called as a bolt connector by selecting the faces which are going to connect and define the connection type and take the pretension into account. How to decide which mesh we have to use in a part and the effect it will make? So it totally depends on the experience what you have with the meshing, what you use, and the result accuracy. So both hexahedral and the tetrahedral mesh are used universally. Hexahedral being robust to solve the analysis, while but it is lag behind the capability where the complex geometry cannot be captured properly in all the area. So in that case, tetrahedrals comes into the picture, and we can use the tetrahedral mesh. So it totally depends upon the how the complex the geometry, the analysis is, what mesh you want. Here we have a total control, like we can create a multiple FEM inside the 3D Experience Simulia tool, and we can do a mesh convergence analysis. Let's say with mesh FEM1, what will be the result? With FEM2, what will be the result, and all. Is it possible dynamic analysis in 3D experience? Yes, we have a total all type of dynamic analysis. That is not limited to just dynamic. We can also do explicit analysis, which is purely highly dynamic in nature or a highly volatile in nature, where there is like an example like a car crashing or a bird hitting the wing of an aeroplane, and due to that the bird is getting scattered. And what is the stress getting generated due to the hitting of a bird on the plane wing? So such type of non-linear analysis or dynamic analysis or a non-linear analysis where there is explicitity can be done inside the 3D Experience Simulia. Yes, we have the capability where we can do a mid-surface extraction inside the same window. So we can select the face, and I can tell the software to extract the mid side or the top face or the bottom face. Yes, sir. We can simulate the solid edge data also inside the 3D Experience Simulia. You just need to either you have a two approach here. You can take the you can connect it with the 3D Experience PLM connector for the solid edge and keep the parametric associativity, or you can convert the data into a neutral file and use it for the analysis purpose. So the last question what we have here was something called the can we solve non-linear contact convergence issue easily? So the contact convergence issue won't actually come into picture here, because we have some high-end tool here where the contact convergence will be totally powered or totally controlled by the solver. Okay, and we have that control how the contact convergence should be done. If there some, let's say if there is a iteration which is failing, what should be the back step should be done. So that control we have inside this high-end tool. How can 2D mesh can be connected with 3D mesh? So we can create a 2D mesh earlier using, let's say, a surface triangle, and that we can use it to convert it into a 3D mesh. So we have a meshing control called as 2D mesh, and then convert a 2D mesh into 3D mesh, which can convert the particular mesh from a 2D to a 3D case. Well, that's all lots of question, and I was really surprised and really happy to answer most of them. Let's say if I miss out anything or you still are not happy with my answer, I would recommend you write us down to the given email ID so that we can answer you for the same. Apart from that, if let's say anyone wants to anyone wants to have a detailed demonstration for the particular tool, feel free to write us down on the below email so that we can have industry specific or let's say your product specific demonstration for you. Thank you for joining the webinar, and I hope you have a very well and have a nice day. Thank you.